we're going to get started with Eirik, who's going to give us the first talk of the night.
Can you hear me? Excellent. Right, this works fine, right? Cool. So I'm Eirik. I also go by Clocks Online. I have these URLs where you can find some other stuff. Today I'm going to be talking a little bit about general parallelism, some iterator patterns, and some what I consider elegant functional solutions to some common problems. I'm going to be using one sample problem from some of our open source stuff. And hopefully it will contain some ideas that should help you speed up your code a little bit, and how some of this should become even better in the futures. So I actually write Rust for these guys here in this very building. The big open source thing I work on a lot is Shipcat, which is our kind of abstraction around Kubernetes. It finds what a microservice is and it controls how to deploy to Kubernetes. I'm going to talk about one particular solution from it because it kind of illustrates this type of problem pretty well, I think. The code of it is all available online if you Google it, but I'm going to be presenting simplified slides from just one function in there. The TLDR of the problem is really that we have close to 500 microservices. That's all sitting in one tightly controlled config managed repo. And to avoid congestion on that, we actually run a lot of, and to ensure it's valid, we run a lot of validation before things are even merged in there. And a lot of that goes through this really tight Rust loop and it's actually performance critical. So the actual algorithm for it in like imperative terms just looks like this. There's one main function validate, the enter point. We call out to a list services thing, which like finds all the manifest that is relevant to a region. I've kind of hidden that detail, but it's doing a little bit of IO. It's reading a subdirectory and reading one file from each subdirectory to make sure that this service actually is relevant to the region we're looking at. And then the stuff that I ultimately want to parallelize in here, the body of the for loop, where I loop over everything in all of the manifests that I found and basically load them, which is a more expensive IO operation where I load everything inside each subdirectory, smash things together, load all the templates that's necessary for the services, and make sure that they're all valid. All the template contexts have the valid stuff that's necessary so that we don't do any Helm upgrade calls that's not valid. And I'm also collecting the result at the end. So this is going to convert into a map once we turn this into an iterator solution. Error handling also initially pretty bad. We're just like bailing at the very first thing. I would really like to just present all the errors that failed so that if you're changing many manifests at once, you can get it all presented to you. So that's all things I'm going to be improving. I've also, for simplicity, hidden like the error type here because it's kind of common that you write your own error type. That's why my result only has one error, one argument. And that's kind of common in your own crate to have like error chain, a failure, or defining your own error enum. So towards parallelism, the unit that we really want to be parallelizing here is our function, which is going to be the body of the for loop. So to convert this into an iterator-based one, I'm just going to show you the slide really, because iterators really just sugars to for loops. So it's easier to see the other way that this is what it turns into. The more subtle part about why this is actually the same is how the error handling is done. Because you can see here, this function is just bailing in the middle of the for loop, whereas this iterator solution here is the map returns, each of the maps returns a result. So you'd expect to have a collection of results, but collect is actually able to transpose that and basically bail on the very first error it encounters. So in fact, this iterator solution is entirely equivalent to this one over here. But I'm going to be making a little bit better. So first off, I'm going to be introducing a little more functional stuff. So I'm going to just be abstracting away this body of the for loop or this map, putting that in its own function that returns the result. It's the same error types with only this pointless OK question mark. And also, if you know the expected signature, so the stuff you put into a map, it's also the same as this very closure, so you don't even need to do that. So that's the point-free style if you're used to that. So that's as much as I really want to simplify this particular thing. So now we're going to deal with basic error handling. So a couple of suggested patterns, if you look at the Rust by example book, which is an excellent thing. Actually, I find it more useful than the Rust book sometimes because it actually gives you the solutions to things you want. In particular, it contains the example of using collect over an iterator of results, but you can also, one of the things they suggest is using filter map on like a function like result is error, and then you get every error inside a vector and you can iterate over those afterwards, which is good, but in this function here, you can see I'm returning a vector of manifest. I actually want to get all the things that was okay as well. And for that, there is another functional tool called partition, which looks like this. It basically categorizes your results into either a left or a right bucket, depending on whether or not it passes the Boolean condition function that you passed into it. So that's good, and you only really need to tell it is, like the turbo fish for this would be weird, so I did it at the beginning. You ultimately really just need to specify that this, the collection that you're putting it into, and the rest is going to be able to infer for itself. Unfortunately, the rest of the type signature is kind of awkward in my opinion, because partition only really categorizes, it doesn't unpack anything. So I am not left with a vector of errors, I'm left with a vector of results, even though every single thing in the left bucket is an error. So to actually use this, I would need to like do all this boilerplate of unwrapping all the OKs or unwrap error, all the errors, or like just if I wanted to throw the first one and collect over it like before. Even like unwrap error is kind of annoying because unwrap error expects a debug implementation on manifest, which I don't have. And I know that this is never going to fail, but you know, that's kind of what you deal with. And you also kind of don't want too many unwraps inside of your code, right? Because it's a good thing to grep for. And in this case, like really a simple pattern matching would have solved this. And thankfully, just like filter has filter map, partition has partition map, and you can do stuff like this. So you can actually do both of the unpacking and categorization at the same thing. So partition map expects you to return an either. Both of these things are things that are not actually part of the core iterator API, and they come from itertools, which is like iterator extension crates. But I feel like this is the real useful thing, and this should so be in the standard library. But yeah, so this is very nice now. You can see I have a vector of error. I've specified it. That goes on the left there. Now, the next thing to make this even nicer is that result and either are actually kind of equivalent in many ways. Like they're both two-part enums over two generic types. The first generic type goes into the left or the OK. The second generic type goes into the error or the right, or I mixed it up. Ultimately, they should be the same in memory. And so if you just had a standardized way of converting between them, and indeed there is this like convoluted line at the very bottom where you're actually able, this is presented by the tools, to convert from a result to an either, and somehow, or for some reason, swapping the order. But that's at least a well-defined standard. That is the same anywhere. So that means you can smash that partition map into a single function using the point-free style, which perhaps looks a little weird if you're not looked at it. It's kind of dense. It kind of means that the map actually needs to return something that is convertible to an either. But once you've used it a couple of times, and I'm now like put it everywhere, so it works out really nicely. And it lets you actually focus on the errors, because it's now just actually the algorithm here. You can see I'm still just throwing the first error, but because I'm using partition, I'm actually forced to go through the entire collection. So just to show that we can do error handling pretty nicely now, I'm just going to loop over it if it's not empty, and return some kind of combination error and print everything. Debug implementation on errors is also pretty good to print in a CLI context, at least in error chain that gives you the stack trace. You might do different things with failure. But yeah, so you do all this kind of normal stuff in there. If you wanted to match on a particular type of error, you can do that in there. But it's all outside of the big imperative part of the loop. So you can handle it all at the end. It takes no time. So I'm just going to package it away into a separate function that takes the error vector. And if that vector it passed in is non-empty, that bails. And so the validate is going to bail. So that is the end of the sequential algorithm. It's now very similar to what we started out with, except we go through the entire thing rather than stopping at the first error, and we turn it into an entirely functional approach. So now we've gone down this abstraction rabbit hole, perhaps. We can parallelize this. And I'm going to cheat a little bit here, and I'm going to import Rayon, and basically don't blink, swap 4 characters and change my iterator into a parallel iterator and import Rayon. So Rayon also actually gives you either and iter tools directly. So so they've kind of said that this should be a standard, I feel. And what is this actually doing? It's Rayon creates a thread pool under the hood with the number of OS threads equal to the number of logical cores. So I know I'm using a data parallelism library for I/O, but ignore that. It kind of scales kind of similarly at the low end. Assuming that, how much speed up can we get from this style of parallelism? So suppose I measured the sequential algorithm, and we found that for one particular region, calling validate took 20 seconds. And we also found that shipget list services, the sequential step before, took 2 seconds. How much speed up can we get from this if we had 4 cores, 8 cores, 100 cores? Anyone like to guess for 100 cores if it took 20 seconds? Sorry? 2 seconds? Yeah. Anyone lower? Anyone higher? Sorry? Yeah. So that's obviously the trap, right? Because if you go back to the imperative, the sequential step, list services, sorry, that's sequential. You're never going to improve that. So no matter how much cores or threads you throw at this, it's never going to go above 2 seconds. So your maximum increase is 10x. And this is not really like a trick question how this works. This is very well detailed in Amdahl's law. The speed up you get from parallelizing an application is entirely dependent on how much is actually parallelizable. In our case, 2 out of the 20 seconds was sequential, so we're following the purple bar here. We can see it's kind of flatlining around 10x improvement. And you can see it gives you kind of a linear increase for the first 4, but then to actually get an 8x improvement, you need 32, which I find kind of unintuitive. Like the fact that you have this algorithm that's 90% parallelizable, and it's actually kind of hard to get to an 8x improvement. I find that kind of surprising. Now, back to the fact that data parallelism, you can tweak Rayon to the number of threads you actually want, so it becomes kind of similar to using your own thread pool. But ultimately, like this is an imperfect solution for I/O no matter how you look at it. Like, it's not really super smart. And to illustrate how unsmart it is, I'm going to be doing the same thing in a Unix system where I'm going to take the part of the algorithm that was sequential, list services, and I'm going to expose that as a subcommand of shipget. And then I'm going to take the parallelizable part, the verification, the iterator, and expose that, chuck out all of the parallelized part of it. So all of this is now sequential. There's no Rayon, there's no thread pools. And I'm just going to call it from bash from a different processes. So I can pass in all the arguments the first way on the first line on the second chunk there. That's the naive way. You just pass all the arguments to shipget validate. That basically performs the same as the imperative solution I presented on the very first slide. Then there's a couple other ways using xargs. The second solution here, also kind of the same. You end up calling shipget verify on each service, so 1,000 calls. And also there's a little bit more performance, but ultimately not really changing it too much. Bash is pretty fast. But the key benefit of this is that you can use xargs batching mechanism, which is effectively you can tell xargs to do 20 processes at a time and also partition the set of services into sets of 20. And xargs is going to make sure that there are at least up to 20 processes running at the same time, and they're all going to get the next 20 available. So you're going to partition this out. You're going to batch everything through xargs. And this actually turns out to be very similar performance-wise to using Rayon tweaked to 20 threads, which it's kind of cool that you can just do this in Bash, because that means this is useful for other things. Like if you needed to speed up code that you're not in control of, like YAMLint, and you need to speed up YAMLint in the repo, you can just pipe the list of YAML files to xargs, and you can get the same speed up from that, which we do, and that's actually very successful. But ultimately, like in this case here, we're now tuning process numbers. So if you're interested in tuning, I would just like to recommend this one talk, which came out last week, about scientifically speeding up your applications. because there's a lot of things when you're doing performance measurements that is very non-intuitive, like how cache misses affect your things, how address layouts affect your things. This actually goes into details on how to do it statistically, which I've never seen before. Super recommended. But in this particular case here, we are just kind of choking on IO threads, and they're all kind of blocking. It's at a certain point there is an overhead to spawning more threads here. So we would need to either make our algorithm better or use our threads in a more effective way. So that is where async is going to come in and fix everything, right? Because nothing is blocking. You can work with less threads and have the same effect. And your thread pool kind of knows when it can resume the work for each future, because you have the concept of a waker. So that's really what I think is the core of async. Like you have a lot more smarter use of the underlying runtime. But I'm deferring to Hypnotoad here because a lot of my examples are a little bit speculative about what's coming up. Because what we really have is just this. That's being stabilized in 6 weeks. So we have tasks like what your workload is, kind of futures, what your workload is meant to return when it finally does so. And then there's all it's the future trait for like how it's going to poll for it, the language extensions for the async keyword, the await keyword, so you don't have to write impl future in all your return types, the pin API, all these like incredibly hairy low-level APIs that I hope I don't have to deal with too much because they are quite difficult. And they took a long time to decide. So are we async yet? It's a good site for figuring out like the history and things and the status of async in general and how we arrived at these things, but it's also so much work. Like there's 3 years of discussions on all of this. And ultimately, as I said, this is not what I really want to be dealing with directly. What I want to be dealing with is streams, which async iterators. And that's entirely, or not entirely, but mostly unresolved. Like that's at least what it says on the site. We have the futures preview crate, which have a couple of extra things for how to build combinators on top of futures. And future preview crate also defines the stream trait, but these are not what's being slated for stabilization, right? Still, people do build on top of it. Tokyo builds on top of the stream trait, and they've built really interesting things like throttling mechanics. So that just because your program suddenly becomes super efficient and is able to do 1,000 requests to some poor service does not mean that service can do that, handle that very well. That's how you can kill Tiller, by the way. Just like do 50 of them. And async STD, on the other hand, is trying to go more functional approach where they try to replicate the streams, the iterator API, sorry. So that means a lot of the API that I've shown before hopefully should just port very well. In fact, they've done a lot of it already. So here is a recap to the solution we got for parallel iterators. I've written down the functions, two of the three functions that we depended on that are synchronous. If partition map makes it into async STD, currently they have some of the stuff. They have collects, so you can do some of the basic thing I did like very early on. But partition map's not yet there. But if you can, then really, ideally, this should just be converting between these two, right? Which is not like a trivial task. You obviously need to propagate the futures all the way down to ensure nothing is blocking, and that's a much larger thing. This is just a top level guy, and then wait for one of the runtimes to provide the combinators. So that's I suspect this. Already just this is going to be much more effective at Rayon or using your own thread pool and tuning the parameters because it's so much more effective at context switching between these threads. But I feel there's a more perhaps pervasive argument for this as well. And so I'm going to zoom in on the 4 lines at the beginning of this function. So what we can see we're doing here is we're awaiting an entire vector to be returned in synchronous. And then we're turning that into a stream that would then start using to do our parallel workload effectively. What if we just started with a stream from scratch? Like if we made list services be able to return an async stream, then you could start this parallel part a lot quicker. And you basically avoid that whole speed bump in Amdahl's law. And I think that's the real key that like this pervasive use of async has a lot of benefits for all your code, really. So this is what I would like my code to look like in the future. It doesn't, but yeah. Yeah, thank you very much.